Hello, my name is Richard Matyi. I'm a professor in the College of Engineering at Florida Polytechnic. I'm also director of our nanotechnology effort. I'd like to talk with you about some new experimental capabilities that are here at Florida Poly. But first, let me tell you a little bit about nanotechnology. Now, nanotechnology is the study and manipulation of materials and structures at the nanoscale. By nanoscale, I mean that that's the region where our unit of measure is the nanometer, which is one billionth of a meter in length. Now that's a difficult concept to understand, so if I just take a strand of my own hair, the diameter of this hair is about on the order of 100,000 nanometers in diameter. So by manipulating materials and structures at the nanoscale, that gives you an idea how small we're working. Now we need special tools to be able to study nanomaterials, and one of the very best for doing this is a technique called X-ray diffraction. Now you may be familiar with X-rays from dental or medical X-rays, but what we're interested in is their wavelength. The wavelength of X-rays is extremely short when compared to visible light. For instance, the peak of the solar spectrum, light is about 500 to 550 nanometers, whereas for X-rays, the wavelength is on the order of 1/10 of a nanometer. Now that size, or that wavelength, is commensurate with the size of atoms and structures at the nanoscale. So that makes it so useful for studying. Now, one of the ways that we study nanomaterials and other materials is by scattering X-rays off of them. Now, if I had, say, a collection of small droplets of amorphous or liquid-like particles, then if I send in radiation into those particles, that light would get scattered in pretty much all directions. However, if I have a crystalline material, one where the atomic planes are regularly spaced, then the scattering will occur only in specific directions. The directions are given by an equation known as Bragg's law, which says that the wavelength of the X-rays, lambda, is going to be equal to twice the interatomic spacing, the d spacing, times the sine of the angle that they are scattered in. It's the sine of theta. So if I send X-rays with a given wavelength into a material with a well-defined crystalline structure, then what I expect to see are special angles where the X-rays will be reflected out. Now, there are many applications of X-ray diffraction. For instance, you're probably familiar with the double helix structure of the DNA molecule. That was discovered using X-rays. Nowadays, many cars and trucks are using aluminum alloys to get greater strength at lighter weight. How do we study the structure of elements in there? With X-ray diffraction. If you have a microprocessor in your cell phone or in your personal computer, somewhere in the manufacturing process, that silicon chip that forms the basis of modern microelectronics, somewhere during the manufacture, extra atoms were added in to stretch the lattice apart so that electrons can flow more easily. How do we measure that strain in the crystalline structure? We do it with X-ray diffraction. Now, exactly what we can study depends on the nature of the material we're looking at. If I'm looking at a bulk single crystal, for instance, I can determine information about its structural perfection or crystallographic orientation. If I have a polycrystalline material or a powdered material, then there's a wealth of things we can learn. Crystalline phase, lattice parameter, chemical structure, stress, crystallographic texture, I can go on and on. If we have thin film materials, films whose thickness are at the nanoscale, we can determine chemical composition, strain, and structural perfection. And then for isolated nanomaterials, we can use X-rays to study their size and shape and their physical and chemical structure. Now here at Florida Poly, we've entered into a strategic relationship with Rigaku Americas. Rigaku is a worldwide supplier of X-ray analytical tools. In one of our labs, we've assembled a collection of tools from Rigaku that we are using to help us achieve a variety of research and educational goals. So why don't we go over and take a look? Okay, I'm standing in front of the first portion of our acquisition from Rigaku Americas. What you see here is a set of 4 Rigaku MiniFlex X-ray powder diffractions. Now this is obviously a tabletop tool. It's used very widely out there for quality control, rapid turnaround materials analysis, a range of applications. And Rigaku recognized early on that instruments like this might be very well suited for our undergraduate teaching mission. So out of the hundreds that go through their applications lab every year, they've isolated 4 of them and sent them along to us so that we can include this analytical approach in our undergraduate laboratory education. So why don't we take a look and see what's inside. Okay, inside here is one sample. You see that we have a multiple sample changer here that allows us to load up to 6 samples. Over here is where the X-ray tube is. There's an interlock shutter so that with the door open, the shutter automatically closes. When this door is closed, shutter opens, X-rays irradiate the sample. Okay? The X-rays that are then diffracted by the sample, and they go off up here where there is a detector. The sample stage rotates through an angle of theta when the detector rotates through an angle of 2 theta. Very common X-ray powder diffraction geometry. Let's go take a look at the rest of our installation. Okay, I'm with 2 other instruments that are part of our installation. The first of these is another Rigaku Miniflex. However, this one is brand new. It has, well, a number of little technical changes that have been made to it that improve its performance. It is also fully interfaced with the most recent Rigaku analytical software. All those changes, hardware and software, makes this instrument really a very fine research tool in addition to the quality control applications and things like that we mentioned before. So this instrument is actually fairly heavily used now for routine research level X-ray powder diffraction analysis. Over here, this is not a toaster, this is an X-ray fluorescence system. X-ray fluorescence is a physical process by which you shine X-rays onto a sample, and that process of irradiating a sample causes the sample to emit X-rays whose energies are characteristic of the elements inside that sample. It's a very simple tool. You can just open up that door, drop in a sample, close the door, the shutter will open, and we irradiate the sample, and then we record the X-ray fluorescence spectrum. Now, X-ray fluorescence is a wonderful non-destructive way of getting chemical information on solids. For instance, working with phosphate rocks that are mined here in Central Florida is an excellent tool for analyzing the chemistry of those input materials. So this looks all very nice. Wonderful X-ray, wonderful instrumentation here. But wait, we have one more tool that we'd like to show you. Our Smart Lab diffractometer. Come along. And this is our flagship tool, the Rigaku Smart Lab high-resolution X-ray diffraction system. This is a true state-of-the-art system that is capable of doing the most advanced materials research and development. You will find an instrument like this typically at a very advanced materials characterization facility. We have one here at Florida Poly. Now, why don't we take a look at what's inside of this instrument. This is what a state-of-the-art research tool looks like. Over here is the X-ray source, an X-ray tube. Over here is a set of interchangeable optics that can condition the beam for different applications. Here is where the sample resides. Over here is where the diffracted beam will go, again through configurable optics, and then into a very fancy, very nice two-dimensional X-ray detector. Some of the things that are special about this, you notice that this gear right here allows us to rock the sample back and forth, and we can do that as it is rotating about this axis. Moreover, the entire detector arm, in addition to moving up and down, along with the tube up and down, the entire detector will swing out, which gives us an added flexibility for a number of materials analysis problems. Now, obviously, a state-of-the-art instrument like the Rigaku Smart Lab is capable of performing a wide variety of tasks. And I have spent my professional career in a number of cases developing those capabilities in other instruments? Well, that takes a lot of time and a lot of work. And so here at Poly, we're trying to do something new. What I've done is I've hired a group of 12 interns, and working either individually or in teams of 2, they are my fingers, they are my eyes, they are developing these techniques. Each student or pair of students is owning a specific technique, a specific capability. And what I'm tasking them to do is to develop a record that consists of the theory behind that technique, how you implement that technique, how you configure the instrument, what sort of samples you can look at, how do you actually go about collecting the data, and then how do you analyze the data. As an example of this, right here behind me is an example of one intern's work. This is a high-resolution double-axis rocking curve, a very common analytical technique in the semiconductor industry. We are doing it here. So what is happening is that all of these interns are going to learn, of course, a fair amount of X-ray diffraction theory and practice, but in addition, they are going to learn what it takes to effectively operate a major piece of instrumentation in a research and development environment. I don't know of any other installation, any other university that has ever done something like this for students at the undergraduate level. But that's just consistent with our philosophy here at Poly. We want to have real tools, producing real data for the real world. That's Florida Poly.